Welcome back, folks. Today we're going to get into lesson 1.2, finding limits analytically. Basically with this lesson we're going to answer all the same questions we did in our previous lesson about limits, except for this time there's no picture for us, there's no table, we don't get to use our calculator. We're going to do everything by hand, we're doing everything analytically. Alright, this video here is going to cover part 1. We're going to work through the first 3 examples from this lesson. Part 2 will cover the rest of it. Here we go. Now, first thing we have is a list of some common techniques, we'll say, for evaluating limits analytically. Now, we've got a 5 kind of part list. We could have made this bigger to cover every single possible case. We could have even made it smaller a little bit, just giving you kind of some decisions, but I'd say we got a good sized list here. Number 1 is going to be always trying to direct substitution. When we want to find the limit as x is going towards some value, see if you can just plug that number into our function, and if it works, okay, you're done. That's kind of the simple case. Now, if direct substitution doesn't work, we can look at factoring and simplifying. We can look at multiplying by conjugates. We can look at using trigonometric identities if there's any trig involved. Or we can try to break things apart using properties of limits and then kind of come on back to the top and try direct substitution again. All right, examples we go through in this lesson are going to basically cover using all these techniques. All right, so our first problem, find the value of each limit analytically. Again, that means no calculator. Now, you can always use a calculator to graph these functions out after the fact to kind of see what that limit looks like, but we want to be able to do these by hand. First one, the limit of this rational function as t goes to 1. Now I'm going to say this is the basic simple case where I can just substitute directly. Okay, no issues with my numerators and denominators. Okay, basic case because the first thing I'll look for is if I plug a 1 into my denominator here, will I end up dividing by 0? No, I won't. Okay, so that gives me a pretty good clue that I can just plug this 1 in, and that's going to be the value of my limit. So what I'll do is I'll substitute 1 for all my t's here, direct substitution. So we have 1 squared minus 3 times a 1 plus 2 on top. All right, 1 minus 2 on bottom. Okay, my numerator turns into a 1 minus 3 would be negative 2, plus 2 is a 0. Okay, we get a 0, but it's okay to have zeros in the numerator. Denominator 1 minus 2 is a negative 1. All right, 0 divided by anything, 0. So we just say that the limit of this expression as t goes to 1 is just 0 here. Okay, again, that's direct substitution. When there's no denominator issues, just plug things straight in. And again, it's okay to have zeros in the numerator as long as there's no zeros in the denominator. All right, next up, let's take a look at part B, and here's where we're going to have some issues with direct substitution. Notice we've got the same expression. This time, though, I want to know what the limit is when t is tending towards 2. And notice in my denominator, I'm having an issue with 2. Okay, so with denominator issues, you might be able to evaluate the limits. You might not. In this case, we will. We'll show you why. When I substitute directly, let's take a look at what we get. We get a 2 squared minus 3 times 2 plus 2 on top. And in denominator, we'd have a 2 minus 2. Again, that's going to give us our issue. Numerator, let's see, we've got a 4 minus 6 would be negative 2 plus 2 would be 0. And 2 minus 2 is 0 again. Okay, 0 over 0, that doesn't tell us anything. We know we can't divide by 0. Now, when I see the 0 over 0 case, we still may be able to evaluate this limit. We're going to call this the indeterminate form. Okay, indeterminate form because it doesn't allow us to determine the value of the limit from the fraction we ended up with here. Now this could be 0 over 0. We'll also see it with infinity over infinity. And really the reason this tells us nothing is, let's say that my limit, some number n, was equal to 0 over 0. Okay, let's think about rewriting that in terms of like a multiplication problem. If this was like a 2 or something on bottom, we could multiply both sides by 2 to kind of cancel out the fraction. That's not technically correct, but let's think about doing the same thing with the 0. If I have 0 times n equals 0, well, I know that 0 times anything equals 0. Okay, so that doesn't give us any information about this n here. That n, that limit could be anything. Again, that's what we mean when we say indeterminate form. Okay, so direct substitution doesn't give us any information, but it looks like there's some factoring we can do, some factoring and canceling with this one. So let's give that a shot. Okay, this one's going to work, but it's not necessarily guaranteed to be the case. It could still be something we can't determine. So let's rewrite this as the limit as t goes towards 2 of this expression factored. Okay, it looks like my numerator I could factor as t minus 2 times t minus 1. Denominator is just t minus 2. That's factored already. All right, what I have then are some factors that will cancel. There's a factor of t minus 2 on top and bottom. Those will go away. So this is really equal to just the limit as t goes towards 2 of t minus 1. Okay, now I've cleared up my denominator issues. Okay, now I can use direct substitution. So I can rewrite this just as 2 minus 1, which is just equal to a 1. There's my value of the limit. All right, so that's our first technique. When we run into this indeterminate form, look and see if we can factor things out and kind of get rid of that denominator issue, and then use direct substitution once you've taken care of that. All right, part C is the same type of problem. Why don't you take a minute, pause the video, work through that in your notes, and then hit play to see the worked out solution and check your answer. All right, next up, let's take a look at part D together. Looks like we've kind of got the same issue with a rational expression. Looks like we're going to have an issue with zeros in the denominator, but here I want to show you a case where the limit doesn't exist. So, right off the bat, let's take a look at using direct substitution. Let's see what happens. Okay, so if I substitute the 2 into this expression, I'd have a 2 minus 5 over parenthesis 2 minus 2 squared. Numerator, we don't get a 0, we get a negative 3. Denominator, we'd have 2 minus 2 is 0. 0 squared is just 0. So we get the 0 in the denominator. But the difference here is this is not our indeterminate form, okay, because we don't have the 0 on top. I'm going to say this part leads to us the limit does not exist. Okay, limit does not exist because if I think in terms of this fraction we ended up with here, if we did have the limit equal to some number, negative 3 over 0, and again, let's think about turning that into a multiplication problem. 0 times n equals negative 3. Well, again, we know that 0 times anything is 0. There's no such number that when I multiply by 0, I could get a negative 3. Okay, that's why we'd say something like this is undefined. In the case of the limit does not exist. All right, next up, problem 2. We're going to take a look at evaluating limits using conjugates to simplify our function, rearrange things, and then use direct substitution. Okay, so let's take a look at what we have here. We want the limit as y goes to 0 of this rational expression with some radical expressions involved in it. Okay, square roots in other words. And you don't have to write this down, but let's just think about direct substitution. If I plugged in zeros for my y's, I would get the 0 on bottom and root 2 minus root 2 is 0 on top. That's my indeterminate form, meaning that I can't work with this in the way it is, we're going to have to rearrange things. All right, we can go down that list, look to factor if possible. This one's not going to factor. So what we'll look to do is use our conjugates, multiply by conjugates, and the way you'll recognize that case is anytime I have roots like square roots, mostly square roots, with some plus and minus in it, we might be able to use conjugates to clean things up. So what I'm going to do here is I'm going to multiply the top and bottom of this fraction, okay, by the conjugate of the numerator. We'll say root y plus 2. Okay, here we have a minus, so we'll say plus y plus 2. All right, conjugate just means that if you have a sign in between your two terms, you just flip what that sign is. And we'll do the same thing on the bottom. So we're multiplying by just a fancy version of 1, not changing anything. All right, and why did I pick the numerator? Well, that was the part with the rational expression, the two-term rational expression, so that'll be the part I can clean up, hopefully. All right, there are some tricks for multiplying conjugates. We'll remind you what those are. But in my numerator, I'm going to have to FOIL these two binomials together. Okay, root y plus 2 times root y plus 2 just turns into a y plus 2. We can think of that as root y plus 2 squared multiplying by itself. So the square and square root will cancel out. That's my first multiplication. For the outer, root y plus 2 times root 2. We could just write that as a plus root 2 root y plus 2. And I'm not going to get into distributing that 2 through here. Okay, we'll show you that canceling in a second here. All right, when I do my inner multiplication then, I'll have a negative root 2 times root y plus 2. So minus root 2 root y plus 2. And that's going to be the thing we're looking to cancel and clean up. Notice I have a plus root 2y plus 2 and a minus root 2y plus 2. Those will cancel out. Those are going to cancel out that inner and outer term every time you multiply by conjugates. So when you're working through a problem, you can probably skip that step, skip even writing those out, just multiply the first and last. We're just putting that in here for your note's sake. All right, then finally, the last multiplication, I've got a negative root 2 times a root 2, which is just going to give me a negative 2 here. Okay, and I suppose right off the bat I can cancel the positive 2 and the negative 2. Those won't necessarily cancel every time, but in this case they do. Denominator then, I'm going to leave things in factored form. I could distribute through, but typically what you're going to look to do is reduce the conjugates by having positive and negatives cancel out, and then just leave the other part of the fraction, whether it's numerator or denominator, in factored form. So I'm just going to write that as y times parenthesis root y plus 2 plus root 2 in parentheses here. So, as we run out of room going this way, we can rewrite this all as the limit as y goes to 0 of what are we left with? A y survived up top, and we have a y times root y plus 2 plus root 2 on the bottom. And we still have division by 0, but notice in this case the y's will cancel. So finally what we can do, we got rid of that division by 0 issue, is we could write this as the limit as y goes to 0 of just a 1 on top, all right, over root y plus 2 plus another root 2. Okay, so at this point, we've gotten rid of our division by zeros issue. Now we're back to the simple problem where we can just do direct substitution, plug in 0 for my y's. That's going to give me a 1 over root 0 plus 2, whoops, plus root 2. Okay, so we've got a 1 on top, and root 2 plus root 2 we could just say is 2 root 2. And AP exam's not worried about rationalizing denominators, so we can just leave it like that. All right, so there's an example of using conjugates to reduce down a function that we can't take of a limit of directly. Okay, and an ugly example there. Part B is a little bit cleaner. Once again, take a minute, pause the video, give that one a shot, and then hit play to check your answer. All right, last thing we'll do in this part of the video is looking at evaluating limits involving trigonometric functions. So once again, find the value of each limit analytically. And here we're just looking for the limit as theta goes to pi of cosine theta. Now I'm going to say part A is our straightforward example where we can just use direct substitution. So the question is, without a calculator, can I find the cosine of pi? And there's a few ways to do this. Let's remind you what our trig functions looked like when we graphed them. We had our cosine function, which started up at 1, dipped down to -1, and made that all happen between 0 and 2 pi, which means this dip will be at a pi, its 0 will be at a pi over 2, and then the other 0 would be at a 3 pi over 2 if we're counting by pi over 2's. That's my cosine function. Don't need it for this problem, but let's throw up sine as well. Sine started at 0 and ran between 1 and -1. Got that all done within 2 pi units once again. So the middle will be pi. First peak will be at pi over 2, and then the minimum would be at a 3 pi over 2. There's sine of x. All right, so if I want to know what the cosine of pi is, I can just come over to my cosine graph, find pi on the x-axis, find where it hits my function, which is at a -1, which is why the cosine of pi is just -1. And why, since there's no issues with this cosine function here, the limit of cosine as theta goes to pi is just a -1 as well. So part B, we have another limit to evaluate involving trigonometry. And part B, obviously, we're looking at a more complicated example. Okay, some trig functions, different trig functions within a fraction. And taking a look at what we have, we're looking at when x goes to 0. Now notice my denominator has just an x in it. So I'm not even worried about what the secant of 0 is. I know we're going to have a 0 on the bottom here. As far as can we evaluate this limit, what's the top going to turn into? Well, let's just kind of add to the notes we're taking in the margin here a graph of a tangent function. Remember, tangent was this guy that had asymptotes at pi over 2 and negative pi over 2. A 0 at 0 here. So yep, if I did my direct substitution, you don't need to write this in. We'd have a 0, we'd have a 0, we'd get 0 over 0, indeterminate form once again. So I can't actually evaluate this, okay, in the form it's in. So we can do, moving down our list of techniques, we can utilize trig identities. And for this one, there's a few simple ones we can use. Kind of running out of room with my face right here. Yeah, we'll just write them here. We can rewrite basically all our trig functions in terms of sines and cosines. Tangent of x, for example, was equal to sine x over cosine x. And then for secant and cosecant, we had secant x is 1 over cosine x, and cosecant x is equal to 1 over sine x. Those were our basic trig identities here that we can utilize to rearrange this problem here. All right, so with trig and fractions, okay, a good first step would be to rewrite everything in terms of just sines and cosines. Tangent, like we said, we can say is a sine over cosine. And secant is a 1 over cosine, so I can rewrite this 2x times 1 over cosine as 2x over cosine x. All right, kind of looks like we made things worse. I've got complex fractions, fractions within fractions, but we can take care of this division by just dividing the fractions, multiplying the numerator times the reciprocal of the denominator and when I do that, I end up with a cosine on top and bottom that we can reduce. So now I can rewrite this as the limit as x goes towards 0 of just sine x over 2x. All right, so I'd say with those trig identities, we significantly simplified the function we're working with. Okay, I've still got my indeterminate form here. If I plugged in 0, I'd have a 0 on the bottom, and then sine of 0 is 0 as well. But we've seen this one before. We looked at it on the calculator, the limit as x goes to 0 of sine x over x. We said it's going to keep showing up for us. We know that's just a 1. So what I have here then is a 1/2 times 1, which is just 1/2 for this limit here. And again, that trick, that limit will be one that you want to memorize. Okay, we'll keep throwing it at you in the homework and the practice sets and stuff like that. So you will memorize it, but there's an example of a limit we already know how to do sneaking into a new problem. All right, let's do this. To finish up this part of the video, there's a part C as well. Go ahead, pause the video, use our simple identities to rearrange that limit, evaluate it, hit play to check your answer then. All right, that's it for part 1 of our lesson 1.2. Okay, that video is plenty long. Go get some practice in here. We'll pick up from there in part 2 of the video. Okay, start working through the homework. Homework stays in the same order as the notes. So just keep going until you get to some stuff you don't know how to do. And like always, if you need help, if you have questions, make sure you are seeking out that help. We'll be here to take care of you. See you later.